Okay, let's go ahead. Next, I'll explain a tangent plane. As you see at advanced calculus, we can define what is a tangent line, and in case of surfaces, we can define a tangent plane. So-called surfaces by honest differentiable geometry by introducing proper patch. Surfaces is simply an orientable two-dimensional smooth manifold. Smooth means this infinite differentiable. So, like a trigeometry function or elliptical surfaces, paraboloid, or torus and sphere, we can think about a tangent plane. Then the question is, how we can define a tangent plane on a infinite, in the case we assume infinite manifold. As I said, manifold are like a surface or curve, an abstract existence. Okay, a line and surface is visible, but manifold is so abstract. So we can think about how well transplant the traditional definition of a abstract manifold. The idea is based on the K algebra. So it's frankly speaking, that is so abstract. So abstract, but in case of abstract manifold, that idea is well applicable. So, if the operator, so to define a K derivation, we need a neighborhood okay, and consider a map that means that neighborhood, we can take a neighborhood at P. There is a function f. As we think about a tangent line as like a tangent plane or tangent line, we can think about df. Okay, like this, we can think about vf. But that is the domain is a real number. You can think about that need a point P. If we does not consider a point, then it is good to define just C infinite. Okay, that is also a function differentiable because that is infinitive differentiable function. That is a differentiable function. That is also differentiable, and if no point P, we can think about VFP. Okay, but if an operator that is arbitrary operator V satisfies, we can think about only this part, satisfies V is K linear, and V satisfies so-called Leibniz rule. As I said, if we yield the value, just consider point P. That is a real value. Okay. But we can consider only function, that part. If we don't know what is a map V, however, if V satisfies this condition, this is very stronger. Or when you see this, oh, this is a differentiable. Okay, even if we don't know what is a V, what is a map V, however, V satisfies this condition, we call the operator V a derivative at P, and the collection of the derivative at P is denoted by the collection of derivative at P is just denoted by TPM. Explicitly, collection of a K derivative. Based on this notation, we explain based on K linear like this. Just okay, like this. Then that is called a tangent vector space, and V is a tangent vector. Okay, that is abstract, but when you think about that is related, deeply related to derivation, we can accept the definition. As I said, that is a part of the K algebra. Even if I explain all about the K algebra, let's see the commutative algebra lecture textbook. Find the commutative algebra. I recommended the Hunger Pearl. On my Instagram lecture, see my Instagram lecture, K algebra. Furthermore, that satisfies a vector space condition, and its dimension, if M is n-dimensional differentiable manifold, that dimensional is naturally, obviously, is n. However, note that the definition based on the neighborhood of point P. As you see, the point depends on the neighborhood, depends on the vector, depends on the coordinate. So because the basis is not unique. That is in mathematicians' view, that's this very annoying. So there are another definition to avoid this problem, so-called germ and stock in algebraic geometry. But that is too more abstract than this definition. But based on the definition, when you define a tangent space with using germ and stock, we can overcome this vagueness, annoying part. And because the tangent space is a vector space, we can think about a bilinear map. Okay, that is vectors. That, guys, is clearly vector space. We can think about following bilinear map such that for any neighborhood with a local coordinate, we can define take a vector, choose two vector, that is written as Gij. Precisely speaking, that is a vector field, local coordinate planes. Okay. That is just any map, but if there exists a bilinear form such that if we can take a map phi, that the guy satisfies symmetry and positive definite, if we find a bilinear map which satisfies the given condition, then we call M a Riemannian manifold, and the map phi is called a Riemannian metric or Riemannian tensor. As you see, that is 2-0 tensor. So that name is also reasonable. Next, in fact, let's think about phi, v, and v. That as you see, that is a metric axiom. Note that norm induces a metric because that guy is vector space. So if we its norm is given, metric is defined if xy is defined like this. However, not vice versa, because that is just a set. Set is need not to be vector space. But in this case, that is a matrix, but these guys is a vector space. In this case, we can think about this part. Because in Riemannian matrix is a vector space. Okay, so how we define? That is becomes as norm. But as you see, V is corresponded to a tangent vector like this or this. Okay, so V, we can, if consider, if you have a curve, if you there exists. Okay, so anyway, we can understand that is if P a particle, in fact a point, and the particle moves along the manifold M, that is V, like a tangent vector. So we can see that is like this. So that corresponds to speed of the particle along the curve. If curve exists, curve alpha. And point P, particle P, depends on the time t, so that differential is well defined. And if we know the curve alpha is also written as alpha prime t. Okay, that is a correspond to speed of the particle along the curve alpha on a manifold M. So if you know the trace of the particle, we can compute a total length from if 2 point is fixed. So when a particle P moves along the curve from x to y. Because this is speed, total length is defined my lecture note is written as alpha and beta. That is not nice because the curve name is also alpha. So anyway, okay. That is anyway the length is defined by like this. Or if we can express the length as a function like this. Anyway, that length is called arc length.